So this is a video about a formula that takes a sum of sine and cosine and turns it into just a single sine. Notice it has a different amplitude and it has a phase shift of phi. And before we talk about the formula itself and how to use it, let's go ahead and look at an animation that shows what we're talking about here. Okay, so here is a graph I've made on Desmos, which is an online graphing calculator. And you can see that I've graphed a plain old sine and a plain old cosine. The way that these work is I can change the amplitude just by sliding this. My sine is red. See how the amplitude of the red graph changes. And then B cosine is green. You can see the amplitude changes, and I can do some negative ones. But if you notice, the black one where I add A sine x and B cosine x, that's moving too, of course, as I'm moving things around. And notice, no matter what the numbers are, that the amplitude of the black graph is different than the amplitudes of the red and green. Also that there's a phase shift, right? So this red graph is a negative sign with no phase shift, and the green graph is a positive cosine with no phase shift, but the black graph, the addition of them all, is a phase shift. Honestly, it could be cosine or sine, but the formula that we're using turns it into a sine. So let's go back to the formula. Okay, so I'm going to go ahead and do my proof. And what I'm going to do is I'm actually going to start by letting these three things be true. So that's how we say, let theta be an angle such that the cosine and sine are as it indicates, and k is this lovely square root. And then I'm going to go ahead and take this right-hand side and I'm going to play with it and turn it into the left-hand side. So there's the right-hand side. I'm going to take this k, and instead of writing k, I'm going to put the square root in there. And then I'm going to use the addition formula. Sorry, that red line messed up. Then I'm going to use the addition formula to rewrite the sine x cosine phi plus cosine x sine phi. And of course, I have a definition for cosine of phi, so I'm going to substitute that in, cross the cosine of phi out, same reasoning, cross the sine of phi out, and instead of sine of phi, I'm going to substitute this value in, just part of the definition. And then when I distribute this square root, do you see how the square roots will cancel? And I'll end up just with plain old A sine x plus B cosine x. Notice I took the right-hand side and I turned it into the left-hand side. And that's proving it. So we have the formula in the box above. And I took all the notation off so we can look at it nice and clean. This is our proof. Okay, so let's do an example now. Because the question is going to always be, what is this k and what is this phi? So here's an example. And again, this is our formula that we're using. We're going to go ahead and use this formula. We've got to figure out k, which is relatively easy, and we've got to figure out what phi is. So according to the formulas, k is the square root of 13 because a is 2 and b is negative 3. Notice this is a minus sign there, and the formula is about a plus sign, so b is negative 3. And because of that, I know that my cosine of phi is 2 over the square root of 13. The sine of phi is negative 3 over the square root of 13. And what's very important about that is don't just use an arc sine or arc cosine. You got to think about it first. The fact that cosine is positive, right? Cosine is positive and sine is negative means that we're in quadrant 4. So however you find the angle phi, just make sure your answer is in quadrant 4, whether you have to do some manipulation of it or whatever you do, make sure it's in quadrant 4. But I know that if I find arc sine of this guy, I will end up in quadrant 4. So that's what I do. Notice I end up with a negative value for phi, and that is in quadrant 4, and I'm done with the problem. I already have my new amplitude is the square root of 13. There's my phase shift, and that would be writing it as a single sine. Now, it's nice to be able to double check your work, and it's relatively easy. What I like to do is graph them both. So if I graph this guy, it looks like that graph. And then if I graph this function, I end up, if you notice, it's the exact same graph. So I'm pretty darn confident that we did it right. And just to make it really clear, this is the answer to writing this value in terms of a single sign. And we're done with the problem.